Welcome back. So we're just starting to talk about statistics, and we've introduced a lot of probability in previous lectures. Now, instead of having a model for the probability of some event happening, what we're going to do is collect data and see if we can infer things about that unknown probability distribution. So the first kind of piece of the statistics puzzle that I'm going to present to you is the notion of randomly sampling from a distribution. Sometimes this is called survey sampling because this is how you would, for example, let's say you wanted a distribution of the heights of Americans. You could go randomly sample a few thousand Americans, measure their heights, and hopefully you could say something about the much larger population from that small sample. Same idea with political polling. You don't want to ask, and you can't ask all, 300 million people what their political preferences are. So you try to do some random sampling of the population, and you use that to infer the things about the larger population that you would like to know, but it's too expensive to measure. Okay? And so that's the notion here, is that there is some large population. I'm going to write this, some large population, and there are actual values for all n of those population numbers. If this is the height of Americans, there would be a very large n, hundreds of millions of people, and each of these x's would be an actual height of each of those people, probably measured in feet and inches. If this was Europeans, we'd measure it in meters and millimeters. Good. Okay, so there is a large population, and the idea is that what we're going to do is we're going to sample a small subset of that large population. So we're going to create a sample of that population, and we're going to sample a smaller, little n number of those people and ask them a question or measure their height or whatever we're trying to infer. And each of those samples now is going to be a random variable because I randomly choose one of these big N people and I ask them. And so there's some randomness to how I generate the sample. So I'm going to generate a set of random variables, big X1 through big X little n, where little n is the size of my generally much smaller sample. Okay, so my sample size is small compared to my population, which is often much larger. And my samples are actually random variables now, okay? So I should probably say, I'm going to walk through kind of some theory about how these sample distributions and population distributions are related. Then we're actually going to fire up some Python code and generate some data and play around with it and see if our intuition for these things holds, okay? So the idea behind pretty much all of statistics really is, can I infer something about a larger population or an underlying process from a smaller sample of data? So this means data. Sample means data. And these x's are random variables because I'm randomly sampling them from this population. Good. Now, things we want to tell about this population. The distribution might be something like a Gaussian normal distribution for things like height, and maybe I would only want to characterize its mean and its standard deviation. Or this population might have a really kind of gnarly probability distribution, but the mean and variance and standard deviation are still going to be useful quantities. So I'm just going to write that up, that generally speaking, I'm still going to want some mean and some variance of this distribution. And similarly down here, I can compute a sample mean, a mean of the sample data and the variance of this sample data and try to relate them or infer these larger population statistics. And this is just the intro. There's going to be a lot more building on this idea. Good. Okay, so let's actually just write down what we mean by the population mean and population variance. These are pretty easy to compute. So the population mean, so let's say population, what we're going to write, we're going to have mu equals literally just the average over all of these values. We average them all up. Okay, so it's 1 over big N. That's how many, elements there are in the population. People were, in the whole population. Sum from I equals 1 to big N of these little x sub i's. That's it. That's the population mean. It's just an average over the population. And the standard deviation, the population standard deviation, sigma squared, this is kind of just like what we defined for probability density functions for PDFs, but here we're doing it over this data. We assume our data, our distribution is an actual set of numbers, not just a function for a probability density. So sigma squared now is 1 over n times the sum, again, from I equals 1 to little n, of the squared deviation of each of these x's from the mean. So xi minus mu quantity squared. Okay, this is kind of exactly how we define variance for a probability density function, but now we're doing the sum over data and the mean of that data. And I'll write down just maybe in kind of orange here that this also equals 1 over n times the sum from I equals 1 to n of the square of each of these little xi's minus the square of the mean. Okay, so the sum 1 over n, yeah, I guess that 1 over n multiplies both of these, and I take the sum just over this xi squared guy here. Okay, good. Or actually, no, it's all of this xi squared minus mu squared is in the sum here. So anyway, this is another expression, and just like in variance, we kind of expanded out. We expanded this out into all of its terms and canceled some out. You can do the same thing here with data. I want you to just convince yourself that this is also true. Good. So these are the population statistics. Maybe I'll just say population statistics. And we also can write down the sample statistics. And what we're going to try to do is relate the sample statistics to those population statistics. So the sample statistics are similarly, almost identically defined. So our sample statistics are defined as the following. So we're not going to use this variable mu or sigma squared because those are already used. So instead what we're going to do is we're going to call the mean of my sample, we're going to call this x bar. Sorry, my marker's squeaky. X bar is similarly just the sum from the average of all of these sample variables. So it's 1 over little n times the sum I equals 1 to little n of all of my random variables. Okay, so it's just the average of my random variables. So you can imagine what we do is we actually grab a random sample. So now these are numbers, and I can average all of those numbers, just like I did in my population. And similarly, I can define the sample variance, this kind of sigma hat squared. We're going to call it hat because it's not sigma squared, it's the sample variance. This is going to equal 1 over little n, sum I equals 1 to, not infinity, little n, of xi minus the sample mean quantity squared. Okay? That looks pretty bad, but that's a little n. We're not sampling to infinity because our sample is never infinitely large, it's finite. And we want to know, this is something that we don't have access to. We assume that there is some mean and variance of our population, but we don't have access to these. We do have access to these sample statistics, and what we want to do is see what can we infer about these blue quantities from these pink sample quantities. Okay, so I'm just about to show you a code of how we actually, doing an actual example, seeing how these things relate. I just want to write down a couple more facts that are going to be really important here. There are big N, choose little n, possible random samples. And we say that each is equally likely. Now, of course, that's not really true. If you're trying to poll, Americans about their voter preferences, clearly there are biases in how you draw these samples. If you go sample from a public library, you're going to get a different cross-section. If you call people on phones, you're going to get a different cross-section. There's all of these these biases that are built into actual polling and actual sampling. We're going to kind of gloss over all of that and just assume that all of these random samples are equally likely. It's easy to randomly access a subsample of the population. Okay. And this is called simple random sampling. So this is called simple random sampling. This is called simple random sampling. And essentially that also, there's another assumption here, which is every time I draw one sample, x1, my population to draw from actually gets one smaller. And as I draw my second sample, my population actually gets a little bit smaller. So technically, this is sampling without replacement. This is without replacement. If you have a huge population, like the number of Americans, hundreds of millions of people, this effect is negligible. But if you have a much smaller population, if this is a few hundred or a few thousand that you're trying to sample from, this finite without replacement sampling does actually start to change your probability. So we'll talk about that later. That's just a detail. And so there are so many questions we can ask. For example, it seems like in the limit that little n goes to big N, this sample mean should converge to the population mean. So for example, this is a random variable. Each of these x's, big X's is a random variable. That means that the sample mean and the sample variance are also random variables. They're functions of random variables. So this has an expectation value, and so does this. This has a variance, and so does this. So what is the expected value of x bar? Does it equal mu? Is the expected sample mean the population mean? What about its variance? How tight is that expectation? How much wiggle is there in this sample mean compared to this population mean? And how does that depend on little n and big N and all of these quantities? Really, really interesting questions. They're going to be super useful when we start characterizing populations from sample statistics. Good. So now I want to briefly walk you through a Python code. We'll have more chance to go through this later when we start asking very specific questions and deriving specific answers. We'll use things like the central limit theorem to talk about the distribution of this x bar. Spoiler alert, it's going to be normally distributed, this x bar centered at mu. That's going to be a key result in the next few lectures. So let's do some coding now. And I'll point out, actually, it's kind of interesting. I haven't really coded up probability and statistics for quite a long time. I did most of this when I was a teenager in Mathematica. So I'm a little rusty in probability and statistics in Python. But I knew what I wanted to code up. I knew that I wanted to generate a large population and draw random samples and calculate these statistics. And in about 5 or 10 minutes with GPT, I was able to get this really good skeleton of a code to illustrate these ideas. So I'm just going to walk you through this, and then I'm going to end, and then we'll dive into these very specific, deeper questions in the next lectures. Okay, so first things first, what we're going to do is we're just going to import our basic libraries here, NumPy and Matplotlib. Then what we're going to do is, this is kind of the core guts of the code. We're going to, I'm going to sample my population out of a Poisson distribution. You can do any distribution, and in fact, the power of statistics is that this population doesn't have to have a well-defined, named, nice distribution. It could be some gnarly distribution of voter preferences or whatever. But for this example, I'm just going to draw this population out of a Poisson distribution, because then we know the answer, it's easy to generate data, and it's easy to play around with these means and variances. Okay, so what we're going to do is we're going to create a Poisson random variable with lambda 10, and we're going to generate a large population of 10,000 individuals, 10,000 samples from that Poisson distribution. Okay, that's going to be called my data population. And then it's really easy to draw a random sample or subsample from that using the random.choice command. So we're going to pull a little n subsample out of my population, and we're going to call that data sample. And then from this data population and data sample, we can compute the mean, the standard deviation of both of these quantities. I should probably have labeled the sample mean is X bar and the sample variance is sigma hat squared, okay? So that's what this basic code does. Let's just run this. And it should actually pop out the answer. So the population mean of those 10,000 individuals is 10.0186, pretty close to the true value that was used to generate the data. And we have a population standard deviation here. The sample mean, that's a much smaller sample. The sample mean is very close to the population mean. And the sample standard deviation is close, but not as close to the population standard deviation. Here I'm outputting sigma, not sigma squared, but they're related, of course. And how big was my n? This was for n equals 200. So that's actually already a pretty big sample of my population. 200's a lot. We know from the central limit theorem that n equals about 30 is close to what we need to start getting some notion of the population, or some notion that this is going to be normally distributed. And we know that as little n increases, these estimates should get better. That's our intuition. And we'll prove that in the next couple of lectures. Good. But these are random variables. X bar and sigma hat are random variables, which means that if I redid this random sample over and over and over, if I resampled from this larger population, I'll get slightly different values of X bar and sigma hat squared. They will, they'll have their own distributions. So it's pretty easy to actually, generate those distributions here. I'm going to do that in a minute. I think what I'm going to do first, this is kind of a side point. What I'm going to do now is I am going to take my sample mean, and I'm going to assume that that's the mean value of my Poisson distribution. And I'm going to generate the best fit Poisson distribution from my sample mean. And I'm going to plot that against the histogram of my population, my actual sampled population. Okay, let's run this. This is kind of cool. So the histogram, the actual histogram here, it looks kind of metal. It's got these weird peaks here. So this is one instance of a Poisson distribution of my population. That's my sample, my population distribution there. And the best fit Poisson from my sample mean is this line. This is the Poisson distribution from my sample mean. Okay, so I took my sample mean, I generated a Poisson distribution, and now I'm just plotting the PDF of that Poisson distribution. Don't ask me why it's called a PMF. I guess that's probability mass function, but I call it a PDF. And you'll notice that they're not perfectly in agreement, but they're close. It's not bad. Okay, this is reasonable agreement between my fit and the actual data. And at the very top of this code, actually you can see it right down here. This code has a specific random seed of 42. And so that is to make this reproducible. You can run this over and over and over and get exactly the same results. If you change that random seed, or if you omit that line, then the population and sample will also change from run to run, and you'll get different agreements between these two curves. Okay, so what I really want to do, again, because X bar and sigma hat are themselves random variables, is I want to repeat this process of randomly drawing samples. I want to repeat this a bunch of times, and I want to see how does X bar change from random sample to random sample. Now, in the real world, you don't get to do that. You just get one random sample. Maybe this is really expensive. Maybe this costs $1 million to collect this data. You don't get to do it a bunch of times to look at its statistics. So what we're going to do later is calculate what the statistics of X bar are from first principles. But here I'm just going to show you a plot, because we can, in this cheap simulation example, we can generate lots of these random samples and generate statistics for X bar. Okay, this is an idea that's pretty powerful, that in simulation, there's a lot of things we can do that we can't do in the real world. Okay, so in this version of the code here, what we're going to do, same basic preamble, but now what we're going to do is we're going to write a for loop, and we're going to generate a bunch of random samples a bunch of times, and we're going to compute these statistics over and over and over again. So I think my little value of m here is 100. So I'm going to do this 100 times. I'm going to draw 100 random samples. And here I'm using a smaller n of 30. So these are small random samples of size 30. And I'm going to generate 100 of these random samples and look at the statistics or the distribution of X bar. And interestingly, this is what we get for the distribution of X bar. Now, it's unclear from this exact example exactly what this distribution is, but we're going to show soon that this is the distribution you get from the standard norm, sorry, not standard normal, a normal distribution. X bar is a normally distributed random variable with mean mu. You can see that its mean value is about 10. So X bar is a random variable that's normally distributed with a mean of mu, and we'll calculate what its standard deviation is as a function of little n and things like that. So we'll see that as little n gets bigger, this distribution should get tighter. In fact, I think I can probably plot that now. Look at the bounds. This is from 8 to 11. If I change this n to 200 like before, we'll see that the bounds got a lot tighter. Now it's 9.4 to 10.4. So the kind of variance of my estimate of X bar got a lot tighter. It got a lot closer to mu when I increased the size of little n, my sample size. So these are the kinds of things you can do in simulation, really, really powerful ideas here, okay? But the idea is that this starts to become normally distributed. I actually don't like my seed of 42, so I'm just gonna remove this and try to run it again. And I'm going to use a larger population of 10,000 here. Let's do this. And this is another instance. And if I run it again, let's see. I'll get another instance of this random variable X bar. And the last thing I'll show you, now I'm kind of hinting at things I'm going to do in the next lectures. I said that this X bar is a Gaussian normally distributed random variable with mean mu and some standard deviation. So we can actually compute that normal. Okay, so this is the normal approximation based on something called the standard error, which is the population standard deviation divided by square root of n. And we can compare this distribution here of X bars to the central limit theorem normal approximation to X bar. And this is what we get here. So you see in yellow, this is the central limit theorem approximation of a Gaussian, and blue is the actual distribution of X bar doing this random sampling a bunch of times to get this distribution. Okay, so let's kind of zoom out here, just kind of going back. We have this notion that we have a large population, some large population, and it has its own distribution. We don't know what that distribution is necessarily. We might, but we might not. And it has its own mean and variance. If I can't actually measure all of those variables, I might take a random subsample, a random sample of a much smaller number, little n, and I compute its sample mean and sample variance. And what I want to do is say things about the population mean and variance from the sample mean and variance. And we're going to use the central limit theorem, we're going to use simulations, and we're going to use things that we learned in probability before to say things about the population in terms of these sample statistics. Very, very powerful idea, cornerstone of modern data analysis, also a cornerstone of machine learning. Think about this. This is data that you're sampling, and you're trying to build some model of a larger, more complex distribution from that data. This is very, very much related to machine learning as well. Okay, all of that coming up soon. Thank you.